Chapter 3. Novice Interactions with GitHub Copilot Under Time Pressure, a Deductive Qualitative Interview Study. Chapter Preamble. After evaluating GitHub Copilot's quantitative effects in Chapter 2, this Chapter 3 furthers Aim 1 through a qualitative exploration of human-aid interaction. Through a human-computer interaction lens, this work describes the nature of the interaction and its impacts on the human programmer through a set of interviews. The qualitative analysis supports a number of studies with similar findings, adding additional focus on novice programmers and time-pressured task scenarios through interview data collected after the programming experiment described in Chapter 2. The results of this study provide context to describe the what and the why of human-aid interaction. Participants' comments allude to unique hazards for novices during time-pressured AI-assisted programming that were not revealed by the quantitative findings from Chapter 2. Authorship, Reuse, and Licensing Statement. This chapter was co-authored with Sarah L. Riggs and explores a dataset that overlaps with Chapter 6, but Chapters 3 and 6 explore different research questions, and Chapter 6 analyzes additional data. For additional information, see the Authorship, Reuse, and Licensing Statement in Chapter 6. All co-authors across both chapters, Sarah L. Riggs, Claire Wood, and Ellis Barnes, provided explicit consent for the inclusion of this chapter in this dissertation. The content from this chapter may appear in a future publication. The license for that paper applies to this chapter. The fallback license is listed on the copyright page for this dissertation. Seeing a full, detailed, qualitative picture of this research area provides an integral foundation for informing policy based on concrete human experiences. This chapter briefly touches on the concept of trust as it relates to human-aid interaction, but there was not sufficient available data to explain trust dynamics in depth. The next chapter, 4, addresses this challenge, concluding Aim 1 with a quantitative analysis of human-aid trust dynamics. Abstract. Adapting computer science education to the rapid advancement of artificial intelligence requires a thorough understanding of how novice programmers interact with and perceive artificial intelligence-driven development environments, AIDS. Numerous qualitative studies have investigated human-aid interaction, but there have been limited attempts to unify this work within a single framework. Here, we reviewed 11 qualitative studies of human-aid interaction and interviewed 17 novices who programmed under time pressure with the GitHub Copilot aid. Using codebook thematic analysis, we synthesized themes from existing literature with interview data to produce a qualitative framework. Our results formalize the interaction patterns of mindlessness and influencing, describe the mixed quality of user interactions, introduce novices' anti-anthropomorphic objectivizing of aids, and stress the importance of prior knowledge for success in aid interactions. We argue why CS educators should apply our research by teaching students to program effectively both with and without aids. 3.1 Introduction. 3.1.1 Background. Modern software development is highly language-based, providing several strong applications for large language models, LLMs. A broad ecosystem of artificial intelligence-driven development environments, AIDS, has arisen around this niche. Aids like GitHub Copilot, Tab9, Amazon Q Developer, and Continue are situated within traditional integrated development environments, IDEs. Other aids like ChatGPT, Google Gemini, and Microsoft Copilot are simply general-purpose chat-based assistants with capabilities useful for computer programming. Increasing use and adoption of aids is changing the role of humans in the software development process. A great volume of the work that programmers previously undertook themselves can now be partially or completely outsourced to aids. However, in computer science CS education, the true complexity of software development is artificially reduced into compact and learnable simplifications in course assignments. Consequently, aids pose unique challenges in CS education, given they can handle the well-understood problem spaces of typical educational programming assignments with unusually high performance. Varied opinions on whether educational value might outweigh potential risks have stagnated adoption of aids in CS education. However, curricula that ignore AI may leave students ill-prepared for careers where they are expected to use aids. 3.1.2 Objectives and Contributions. To properly inform CS pedagogy, it's critical that research can better explain how novice programmers use and think about aids. Many studies have provided qualitative analyses of aid use by programmers of varying ability levels, but no work to date has performed a qualitative analysis based on this full body of existing literature. Finally, only a handful of prior studies provide qualitative analysis focused specifically on novice programmers. Further, none of these enforce time pressure like that faced by students working on graded assignments. To bridge these gaps, this work analyzes interview data according to the existing qualitative knowledge base of human-aid interaction. We collected this interview data after having 17 novices program with and without the GitHub Copilot aid under time pressure. Our investigation centered around the following research questions. RQ1. How do novice programmers and aides interact while programming under time pressure? RQ2. What factors can explain how novices use aides while programming under time pressure? RQ3. How does using an aid under time pressure affect a novice's thoughts and feelings? 3.1.3 Summary. Our qualitative framework ultimately included 6 topics relevant to human-aid interaction: interaction patterns, interaction quality, work allocation, appraisals, anthropomorphism, and prior knowledge. The selection of these 6 topics is described in section 3.4. In addition to confirming themes derived from prior work, our analysis formalizes several new themes, revealing the objective, aimless, and passive and fraught interactions novices have with AI when programming under time pressure. We also demonstrate the positive impact of aides and illuminate the road ahead for educators hoping to bring aides into the classroom. 3.1.4 Statement of Theory. Despite value, drive, and strategic observant participation, novices programming under time pressure interact superficially, aimlessly, and passively with AI code generators, leading to subordination, suboptimal reliance, and underwhelming rapport. 3.2 Method. 3.2.1 Literature Review Data Collection. We performed a targeted literature review to understand existing qualitative ideas relevant to our research questions. The inclusion criteria for a paper were as follows. 1. Was peer-reviewed publication. 2. Used qualitative content analysis. 3. Pertained to using AI for programming. And 4. Reported data from human users, other than the authors themselves. While many researchers discuss and experiment with aids, few recruit human participants as part of their studies. Due to the even smaller number of studies exclusively recruiting novices, we chose not to make this a criterion for inclusion. The review began with 2 highly relevant papers, the seminal qualitative study of human-aid interaction by Barkey et al., and a more recent qualitative work studying novices by Prather et al. From there, we used Google Scholar and Research Rabbit to perform snowballing and periodic updating for work published during the analysis process. The first several papers were independently reviewed by the first author and 2 research assistants, who convened to discuss and refine the initial codebook. Further reviews were performed by the first author. In the end, the review consisted of 11 studies spanning 3 years and including data from 217 study participants and approximately 500 survey respondents or social media users. Because this review was an integral part of the data analysis process, we chose to defer introducing this work to section 3.3 below. Additionally, reference to these studies is included as results in section 3.4. 3.2.2 Experimental Interview Data Collection. To expand and evaluate our qualitative framework, we analyzed interview data related to our research questions collected as part of a previous study. See reference 17. No data from the previous study was included in this analysis, and no data presented in this analysis has been reported previously. Participants and context. 17 undergraduate students taking Introduction to Programming CS1 at a large U.S. research university participated in the original study. The procedure entailed 80 minutes of programming in Python, divided between 2 trials with Standard IntelliSense Autocomplete and 2 trials with the GitHub Copilot Artificial Intelligence-Driven Development Environment, AID. Participants were under time pressure to complete as many tasks as possible within each trial and were incentivized to perform their best through additional prize compensation awarded to top scorers. They were trained to use the aid and shown both risks and benefits of using it, but were intentionally not given any guidance on how they should use it. Additional details on the study design can be found in the original publication. Procedure. After completing all programming trials, participants were interviewed about their experience. The first author conducted all interviews using an interview guide written according to reference 4. The questions that produced the data for this analysis are listed verbatim in Appendix A, but the interview style was semi-structured and not time-limited. Member checking was performed frequently throughout all interviews to facilitate valid interpretations during analysis. Interviews were audio recorded and transcribed, first using automated transcription and then again by a research assistant. 3.2.3 Data Analysis. Preparation and Refinement. Each interview transcript was independently read and highlighted by the first author and at least one research assistant to select relevant and meaningful artifacts. The 3 analysts at this stage reviewed others' highlights and consulted to resolve disputes and generate a list of 466 artifacts. There was no balancing of the number of artifacts gleaned from each participant or size constraint on each artifact. Codebook Thematic Analysis. We performed hierarchical codebook thematic analysis, TA, using an iterative process based on the deductive paradigm, but including an inductive step to go beyond existing work. Codebook TA allows researchers to use themes as both inputs and outputs of the analytic process. The goal of the analysis was to understand the data against a predetermined framework, but acknowledge the subjectivity of the analysis process rather than striving for high coding reliability. As such, the first author was the only analyst at the TA stage, an acceptable practice for Codebook TA. For further discussion on our efforts to mitigate threats to validity, see Section 6. The process began with the initial codebook developed collaboratively during the literature review, see 3.2.1. All interview artifacts were then analyzed 3 times. Techniques employed included descriptive, axial, emotion, values, pattern, process, verses, and typological coding. In addition to semantic, explicit themes, we provide some extrapolation to latent themes insinuated by the tone or subtext of participants' words. The first pass at the data was a familiarization step. The second was an initial coding and expansion of the codebook to cover novel ideas. Before the third pass, the literature review was revisited against new ideas and the codes were merged and organized. This was necessary because prior work often mentioned or observed ideas in passing that we formalized as part of our analysis, but not during the initial literature review. For the final pass, artifacts were relabeled against the updated codebook, and artifacts describing or implying the manifestation, i.e., number of occurrences, of event-based themes, were marked. Event-based themes, those under 3.4.1 Interaction Patterns, 3.4.2 Interaction Quality, and 3.4.3 Work Allocation, were themes whose significance differed based on whether they truly happened or were merely discussed. For example, if a participant were to say, quote, "Copilot helped me code faster," end quote, explicit, or, quote, "Copilot helps you code faster," end quote, implied, we note this as a, quote, occurrence of acceleration. In contrast, the phrase, quote, "I can see how Copilot could teach you something new," end quote, would be an example of the teaching subtheme, but not an occurrence. For non-event-based themes, 3.4.2 appraisals, 3.4.5 anthropomorphism, 3.4.6 prior knowledge, any matching artifact was considered equally important. Summative analysis and reporting. We also performed summative analysis for the top-level themes using frequency counting and employed matrix displays to find the event-based themes that occurred most frequently. See 3.2.3 above. Topics that occurred and were discussed more frequently appear earlier in the results. The organization of the codebook was based on thematic affinity, so high-level themes were not necessarily more prevalent than lower-level subthemes. For example, the humanizing theme consisted of just 8 quotes, while the evaluating by pattern matching subtheme of insourcing alone consisted of 14. Readers are encouraged to consider the breadth of ideas cataloged in addition to the frequency of these ideas within our data. Well-established codes were derived from prior work, and novel themes were named based on our interest in the implications of aids on computer science education and the content of our unique dataset, not necessarily derived in vivo. Where a citation appears beside a code in the results, that code was borrowed from the authors of the reference work, for example, in Table 3.1. Where possible, codes were formed as gerunds, i.e. process coding, other nouns, or short phrases that most succinctly captured the theme's meanings. References to thematic topics and top-level themes included in our framework are denoted by code words in bold, while lower-level subthemes are shown in italics. For brevity, we use the word theme loosely in reference to the codes which denote the themes themselves. Strictly speaking, themes are not often fully explained by the code words, so readers should refer to the explanations for each code throughout the results and referenced works. Quotes in section 3.4 were taken directly from transcribed interviews. Some quotes contain omissions indicated by ellipses or paraphrasing indicated by italics, but never with the intention to alter the meaning of the original text. Quote selection statistics, see Appendix C, were tabulated and used during the writing process to balance representation of all participants to the best of our abilities. 3.3 Related work. Our literature review focused on the qualitative portions of 11 peer-reviewed papers, see Table 3.1, published between 2021 and 2024. These papers mostly contributed qualitative-only analyses, but 4 had substantial quantitative analyses as well. These studies explored user interactions with the GitHub Copilot aid specifically, while one more used GitHub Copilot along with several other off-the-shelf program synthesizers. 5 other studies focused on evaluating or understanding user interactions with custom aid prototypes. Finally, 2 studies performed analyses of larger-scale survey or social media data. Aside from these 2, all the studies recruited human participants for their data collection. The number of participants ranged from 11 to 42. Mean 24, median 28, total 217. Python was the predominant programming language, but the exact nature of programming tasks varied widely, as did the qualitative techniques employed. A few high-level findings were common across several studies. 1. Aids are useful but also imperfect. 2. Prompting aids effectively is challenging. 3. Users are tasked with evaluating AI-generated code. And 4. Users over-rely on aids despite holding moral stigmas against doing so. Because details from these studies are reported in the results, section 3.4, we focus here on the roles of time pressure and ability level in prior work. 3.3.1 Time pressure. Only 3 studies enforced time pressure while users interacted with aids. For these 2, participants were given synchronously timed programming tasks in 20-minute sessions, while in reference 21, participants worked on 2 tasks asynchronously over 1 week. Other studies allowed participants to use aids at their own pace. This design choice limits ecological validity, as both students and software professionals work under time constraints in the real world. Research in other domains has demonstrated how time pressure can cause users to rely more on AI, harming performance when the quality of the AI assistance is poor. One participant from reference 34 believed that the aid they used would have been more helpful if they had not been under time pressure. Zhang et al., who enforced asynchronous time pressure, suggested that a novelty effect may have caused users to engage more with the aid than they otherwise might have. Having abundant time, perhaps they felt comfortable to fully explore and enjoy the aid's capabilities. By comparison, several participants in reference 51, quote, perceived a loss of control, end quote, using the aid, perhaps due to the synchronous time pressure they faced. Participants from all 3 studies enforcing time pressure reported some negative experiences trying to use or understand aids, suggesting that time pressure may indeed amplify negative experiences compared to conditions without time pressure. Therefore, the current knowledge base is limited in that it focuses mostly on untimed, low-stakes interactions. 3.3.2 Ability level. Within the novice level, 3 studies captured the range of programming experience. Kazemadabar et al. Recruited youth with no prior text-based programming experience. Braither et al. Recruited CS1 students, and Jai Gopal et al. Recruited CS2 students. Other studies' data came from participants of unknown, in the case of reference 34, or ranging ability levels, with a strong skew toward advanced programmers. It's difficult to know which findings are general and which may be specific to users of certain ability levels, as the studies focused on novices share many findings with other studies. However, it does seem that novices relied heavily on aids, struggled to interact with them effectively, and tended to use the simplest and most obvious features available. An accurate qualitative model of novice interactions can draw on theory that applies also to advanced programmers, but should be validated against data specifically from novices. 3.4 Results. Our hierarchical codebook thematic analysis, see 3.2.3, yielded a multi-level qualitative framework co-constructed from both prior work and our interview data. Table 3.2 summarizes 6 identified topic areas and their associated top-level themes. For brevity, lower-level themes are omitted in Table 3.2, but further explored within each subsection. Figure 3.2 shows an overview of the framework in an idea map format, stressing the interconnected nature of the various high-level themes. Throughout the remainder of the results, we discuss examples of each top-level theme from both prior work and our interview data, denoting topics and top-level themes in bold and sub-themes in italics. The 6 topic areas were identified post hoc to better organize the disparate themes in our framework. The full hierarchy can be found in Appendix B, Qualitative Codebook for Chapter 3. The framework is presented here as a top-down outline of the hierarchical codebook according to prevalence within our interview data. Event-based themes that occurred often were given precedence over ones that were merely discussed often. See 3.2.3 for further detail. The topics we use to categorize the themes are as follows. 1. Interaction patterns. Describe how a human approaches and engages with an aid and how the aid affects the user in return. This topic is a frequent focus within prior studies. 2. Interaction quality. Describes humans' positive and negative experiences during or after using aids. This topic was inspired by the ranging quality of users' interactions with aids across the literature, see Table 3.4, but also mirrors the positive and negative emotion subthemes in Reference 40. 3. Work allocation. Covers how a user divides work between themselves and the aid. Mastering this division is the key to unlocking the ever-improving power of aids. The origin of this topic is best credited to Prather et al., who formalized how users outsource work to an aid. 4. Appraisals. Describe the systems of value humans use to assess their own abilities, to trust aids, and to judge how to use aids responsibly. We group these together because they're subjective value judgments rather than positive or negative experiences. While no prior work has grouped these ideas in this way, several studies have touched on each of these themes. See Table 3.6. 5. Anthropomorphism. Explains how people think about aids either as social agents or as inanimate tools. This role dichotomy was introduced by Ross et al. In Reference 43. 6. Prior knowledge. Pertains to how humans expect aids to act, their competencies programming and using aids, and what biases they hold toward aids. This topic helps explain what gaps education needs to fill for novices to have successful aid interactions, and aligns well with Guideline G5 of the 18 Human-AI Interaction Guidelines in Reference 1. Quote, ensure the experience is delivered in a way that users would expect given their social and cultural context. End quote. 3.4.1 Interaction Patterns. In this section, we discuss 6 interaction patterns that describe key aspects of how human-aid interactions take place. As shown in Figure 3.2, shepherding and mindlessness are human-centric patterns, while influencing and acceleration are AI-driven patterns, and exploration and mirroring are initiated by humans but fulfilled by AI. Table 3.3 shows each of the 6 themes and their first-level subthemes organized by the number of participants who reported or implied an occurrence of the pattern, event-based to count. For further information on the reporting of prevalence, refer to section 3.2.3 and table 3.3. Acceleration. Barkey et al. Introduced acceleration as the first of 2 aid usage modes. In this mode, programmers work quickly and fluidly as the aid helps them carry out their own plans. We expand this idea to include any instances where an aid is used for the purpose of efficiency or speed. See, quote, speed in Reference 40. For example, Jayagopal et al. Quote, these participants all initiated synthesis rapidly and were able to see synthesis results immediately, end quote. Liang et al. Participants described, quote, an AI programming assistant's ability to, quote, speed up work, end quote, end quote. Our participants most commonly discussed interacting with Copilot for acceleration, especially while taking advantage of Copilot's inline completion feature to autocomplete lines of code and comments. Interview I-16, quote, when I was doing things with a counter or something, it would kind of just instantly know how to do that, and that was helpful, end quote. Interview I-19, quote, even the ones I knew how to do myself, I can do it faster with Copilot, which I liked, end quote. Interview I-24, quote, there's a test that asked me to do something with prime numbers, and Copilot just did that in a really short amount of time, end quote. Shepherding. Many of the strategies participants use to work more effectively with Copilot fall under the theme of shepherding. This theme was introduced in Reference 40, but relaxed here to include similar frequently observed behaviors. By prompting Copilot with comments and with code, participants provided context to improve suggestions as in prior studies. Jiang et al. Quote, participants use natural language by itself as their primary strategy, end quote, and often reworded requests to get better results. Interview I-11, quote, I would create a comment, and at some points I would use part of the instructions, and I saw Copilot was able to see what I was going for, end quote. Interview I-12, quote, giving it information but not too much information, literally what you want it to give you, and less is honestly better, end quote. The data also strongly represent that shepherding is an acquired skill. When asked about reaching a rhythm using Copilot, several participants, I1, I12, I15, I16, I19, I43, said it took until their second trial with Copilot for this to happen. They also shared speculations about how this skill might continue to improve with further use. These ideas align with the findings of other prior studies discussing the importance of prompt engineering. For example, references 11, 18, and 34. Nam et al. Quote, participants appreciated GILT's ability to easily incorporate their code as context, but some participants reported that writing a good prompt is still a challenge, end quote. Scotia, Hacker News, post 35853949. Quote, using ChatGPT to code effectively requires internalizing the small sliding context window and correct specification of the problem space, end quote. Interview I-20, quote, I think if I used it more, I would get better at knowing when to use it, end quote. Interview I-42, quote, I definitely think I can get there with time, end quote. It was also my first time using it. I just need to get used to it and how it works. Quote, just understand that a little bit better, end quote. When Copilot's outputs were not correct, participants employed adapting in attempts to move the code closer to being correct, as in other prior studies. Kazemadabar et al. Quote, we identified 175 cases in which learners correctly modified the AI-generated code to align better with the task's requested behavior, end quote. Interview I-4. If the code, quote, generated an error, I'd be able to stop and correct it, end quote. Interview I-47. You need to, quote, be able to tweak it when it can't do what you want it to, end quote. They also shepherded Copilot using backtracking, i.e. restarting a task or deleting portions of their work like in prior studies. Vaithillingham et al., participant P1, quote, because I did not understand several parts of the function, I did not know how to debug the function. This caused me to get rid of the whole function generated by Copilot and start over, end quote. Interview I1, quote, if I get started on my own and it ends up not being the correct way, the only way to get unstuck in that case would just be to restart and delete everything, end quote. Interview I-19. If it didn't pass the tests, quote, I would try different strategies. Maybe I'd try my own code and let it fill in the rest. Or I just tried a different solution, end quote. Others mentioned behaviors consistent with drifting, which we categorize as a maladaptive form of shepherding, rather than its own behavior altogether, as in reference 40. Therefore, quote, accept and adapt, end quote, drifting is a type of adapting, see above, and ideas related to, quote, deciphering, drifting, can be found between overload in 3.4.2 and evaluating by inspection in 3.4.3. The drifting pattern itself consists of users making repeated unsuccessful attempts to shepherd the AI, wasting time. Scotia, Hacker News, post 34703814. Hallucinations, quote, can be particularly hard to detect, resulting in a frustrating experience. Quote, I burned an hour with ChatGPT, end quote, end quote. Interview I-11, quote, I would go down a route with Copilot and it just didn't make sense, and then I would go back and I would try to do it another way, and sometimes it suggested the same pathway, end quote. Interview I-42. I got sucked into paths that didn't work, and, quote, found it difficult to get out of that hole. Usually, I'm pretty good at thinking of a different way to solve something, but here I couldn't think of anything, end quote. Prather et al. Described their participants using another form of shepherding they call slow accepting. Prather et al., quote, here participants would type out Copilot's suggestion, often character for character, without outright accepting it by pressing tab, end quote. Participants I-10 and I-12 believed shepherding by slow accepting to be a deeper way of engaging with suggestions than outright accepting. However, only I-10 indicated they used this strategy. Finally, we did not find any examples of shepherding by decomposition in any of our artifacts, despite abundant evidence of it in prior studies. Ross et al., quote, other participants approached the programming challenges in a piecemeal fashion, breaking them apart into a set of smaller tasks, then invoking the assistant to aid with each one, end quote. Mindlessness. Participants often approached interactions with Copilot without careful planning or forethought, an ideal we call mindlessness. Liang et al. Quote, many participants reported not employing any strategy as they found AI programming assistants to provide helpful suggestions without needing to perform specific actions. End quote. Interview I-9. I probably wasn't using any strategies I was, quote, consciously thinking about, just things that came in the flow. End quote. For example, 3 participants, I-10, I-11, I-5, described not using certain features that might have improved their interaction with the AI simply because of forgetting about them. As in prior studies, many other participants experienced tunnel vision for the automatic inline suggestions from the AI, opting not to try more involved strategies like looking through the multiple completions panel. Jagopal et al. Quote, although the Copilot pane, which shows additional suggestions beyond the autocomplete one, displayed 2 correct synthesis outputs, the participant did not realize and continued with their own strategy of renaming the function. End quote. Interview I-5, quote, I never actually went out of my way to look at, end quote, panel solutions on the right. Quote, I would just look at it if it was popping up as I was typing and then see if that's what I wanted, end quote. Interview I-2, quote, I prefer to use the inline suggestions. I think it's kind of convenient to just tap tab, end quote. A similar challenge was myopia, a failure to think ahead or look at the bigger picture. Copilot can encourage short-sighted thinking since it provides code that is likely to come next, even when lacking complete context. Prather et al. Quote, Copilot mainly gives students feedback on, quote, where to next, end quote, end quote. Interview I-15, quote, it gives me the answer and I already feel like I could have done that, but I'm taking this suggestion because I know that's what happens next, end quote. Interview I-42, maybe my problem solving was slower with Copilot because, quote, when I do it by myself, I make more of a plan before, and with Copilot, I kind of just jumped right in, end quote. Participants also reported rushing through tasks due to time pressure, causing them to seek rapid forms of help from Copilot and engage more superficially with the code. Fittingly, this idea came up in one of the 3 prior studies which enforced time pressure. Nam et al. Quote, participants prioritized completing more tasks rather than fully understanding the code, as reported by participant P18. Quote, GILT, which could definitely help one to tackle the task better if there weren't under the timed settings, end quote, end quote. Interview I-16, quote, the timer was stressing me out, end quote. I was thinking, quote, do I have enough time to look through these panel suggestions, end quote. Interview I-43, quote, when Copilot solved it, it was nice because I was able to move on and not think about it, end quote. Influencing. We identified influencing as a converse pattern to shepherding. AI can, quote, steer the user just as the user can, quote, steer the AI. White et al. Quote, meta-information can help, quote, steer human activity, complementing Louis et al.'s notion of how humans may, quote, steer the output of a generative AI model, end quote. Interview I-12, quote, I feed Copilot and then Copilot feeds me, so it's just me going back on my own thing, end quote. Oftentimes, this influence came in the form of Copilots distracting participants from their own problem-solving approach, abandoning or changing it based on input from Copilot. There were 3 main types of distractions. The first was when Copilot was polluting a participant's thought process, corrupting their own plans. Barkey et al., participant P16, quote, I was about to write the code and I knew what I wanted to write, but now I'm sitting here seeing if somehow Copilot came up with something better than the person who's been writing Haskell for 5 years, end quote. Interview I-10, quote, sometimes it really confused me because it was telling me to do something and I would think maybe I should do it this way, end quote. Interview I-47, quote, your eyes are going to read it before you can think. You're just naturally going to gravitate towards the words that it comes up with. It distracts you from coming up with something that might be different, end quote. The second type of distraction was rerouting, where Copilot changed a participant's plan but without necessarily compromising performance. Interview I-20, quote, with one where I used Copilot a lot, I was probably going to do it a different way, but I did adapt based on what it was giving, end quote. Interview I-15, quote, I tried taking its suggestions just to see where it would be going with that, but well, its code just didn't make sense to me, end quote. The third type of distraction was Copilot's tempting a participant to disengage with the task and outsource the work. Prather et al., participant P13, quote, "It keeps filling up the screen with suggestions, and I'd be tempted to follow what it's saying instead of just thinking about it," end quote. Interview I-43, quote, "I stopped thinking about the tasks as much, and my first instinct would be to try to just get Copilot to do it, and then if it didn't work, then I would start thinking about the question," end quote. Interview I-9, quote, "It's a lot more tempting to not focus as much on learning when you know that something else is already there," end quote. Another form of influencing participants mentioned was exposure to a wide variety of programming methods. This effect happens often during the exploration usage mode, see 3.4.1, but is a side effect of usage rather than a usage mode itself. Whites et al., quote, "Alternate translations had additional explanatory power in helping participants understand the nature of the underlying code," end quote. Interview I-4, quote, "Copilot is pretty creative in the sense that it can think of things that maybe humans can't, because we have one method or way of solving a particular problem, but it can generate a lot of variations," end quote. Interview I-12, "A downside of giving Copilot too much information is that it would, quote, branch almost, because if you have a small place, then it can only go one stream, but if you have a big place to grow, then it can go 4 or 5 different places with it," end quote. The last major type of influencing discussed was teaching. Although only experienced during the study by 2 participants, I-10 and I-15, many others speculated about Copilot's ability to help them learn better. Even participant I-13, who was generally unimpressed by Copilot, believed it could help them with learning. Ross et al., participant P15. "It's hard to remember hundreds of APIs, but with AI, I think, quote, I'd learn new devlang and new libraries/frameworks faster," end quote. Interview I-10, quote, "I know what max is now. I think I would know it just by looking at it, but now I know it's a command I feel like I could use," end quote. Interview I-13, quote, "I think Copilot would help with memorizing some functions," end quote, "and that would be more beneficial than harmful to learning because, quote, you would still see the function being typed out," end quote. Finally, 2 participants mentioned Copilot influencing their coding style, the form their code took. In one case, I-12, the code was more complicated than it otherwise might have been, and in the other, I-47, there were more comments due to prompting. Barkey et al. Mentioned 6 of their participants who demonstrated this idea. Barkey et al., participant P6, quote, "The kind of comments I would write to Copilot are not the kind of comments I would use to document my code," end quote. Exploration. Many participants use Copilot for exploration of new ideas. The multiple completions panel was often helpful in this mode, though inline suggestions could be as well. Sometimes participants would accept the code they found, but other times they were simply consulting. Kazemnabar et al., quote, "We identified 26 instances in which learners used the AI-generated code as an example, instead of replacing their code with the newly generated code," end quote. Interview I-19. "Usually I use Copilot when I had, quote, written some code, didn't know how to proceed, then I would either use the inline feature or find code from the panel," end quote. Interview I-47, quote, "There were 2 instances where I went to the panel and compared a few," end quote. "I think it's pretty useful that the panel gives you, quote, different kinds of solutions," end quote. Other than looking at new ideas, participants discussed exploration for the purposes of getting started on a task or getting unstuck from an impasse. Vithillian et al., participant P1, quote, "Copilot's function/line generation is a helpful reference. Even if the generated code is not correct, it can point me in the right direction for completing the task," end quote. Interview I-1, quote, "It was really good for giving me an idea as to how to get started," end quote. Interview I-2, "Maybe I would try only to use Copilot, quote, whenever I get really stuck on a programming assignment," end quote. Mirroring. The last interaction pattern, mirroring, appeared in only a handful of artifacts. This is a phenomenon where the output of generative AI reflects the quality of the input. As far as we're aware, it was first discussed in the context of our literature review in reference 18, but is first named here. Jiang et al., participant P4, quote, "My first language is not English. I actually prefer to use HTML language instead of typing the English because I'm worried about, quote, what if I make a grammar mistake? Will it still generate the code for me? End quote, end quote. Interview I4, quote, there was one case where it didn't help me because my code originally wasn't correct, and I changed my code from the beginning just a little bit, and then the answer that Copilot generated was good, end quote. Interview I12, quote, if I feed it wrong information or I write something wrong, then it just makes it a lot harder, end quote. 3.4.2 Interaction Quality. In this section, we discuss the two sides of interaction quality programmers experience using aids, dissonance and harmony. Their subthemes help to explain from the human perspective what causes an interaction to go well or poorly and how a user feels as a result. Table 3.4 shows first and second level subthemes of dissonance and harmony organized by the number of participants who reported or implied an occurrence of the given interaction quality, event-based to count. For further information on the reporting of prevalence, refer to section 3.2.3 and table 3.4. Dissonance. Participants very often experience dissonance in interactions with Copilot. While we chose this code name, this theme has unsurprisingly been observed many times previously. The primary reason for dissonance was misalignment between participants' desires or needs and what Copilot would do. By Thillingham et al., participant P1, quote, Copilot generated a complete function to fulfill the task, but part of the function did not work as desired, end quote. Interview I5, quote, normally when I get stuck, I'm just really stuck, and even having Copilot wouldn't really save me, which it didn't in a lot of cases, end quote. Most of the time this manifested as output that was unhelpful or caused confusion, such as when showing unfamiliar programming constructs. Interview I13, quote, I thought it wasn't very useful for me for the tasks I was doing, end quote. Interview I24, Copilot gave concise code, but not in a good way, quote, more like harder to understand what exactly it's trying to do, end quote. Interview I11, quote, I would go down a route with Copilot and it just didn't make sense. There were parts of the language I hadn't seen before and it confused me even more, end quote. Some also complained that too much information from Copilot caused them to experience overload. This led them to disengage because they did not want to spend time processing excessive content. Barkey et al. Participants, quote, P4, P6, P7, and P13 did not like the multi-suggestion pane popping up in a separate window stating that it added to their cognitive load, end quote. Interview I24. Some of Copilot's suggestions were, quote, super long and complex, and I didn't really take the time to try and analyze quote, oh, what's it trying to do, end quote, end quote. Interview I43. I didn't like the panel as much as the inline because for the panel suggestions, quote, I would have to read through and see what each one would do, end quote. Errors and bugs in the code were another cause for dissonance. Not only did participants mention issues with Copilot's code being incorrect, but some were also bothered by its enabling issues in their own code. Ross et al., participant P28, quote, it makes mistakes often enough to be not very practical, end quote. Interview I11, quote, I can tell that Copilot does have some errors, so you definitely have to double check, end quote. Interview I5, quote, Copilot is not super helpful in terms of it won't tell you if you're totally going on the wrong track or if there's a way better way to do things, end quote. In addition to misalignment, a few participants also mentioned how dissonance could be emotional reactions like shame or emptiness. Interview I15. Talking to Copilot through the comments, quote, blew my mind. I was like, quote, this feels like a violation of the honor code, end quote, end quote. Interview I11, quote, I was more negative and upset when I used Copilot. When I finished the code by myself, there was this achievement that I felt, this goal that I met, but with Copilot, I didn't. It wasn't there. It was empty, end quote. Another form of emotional dissonance was frustration, a common feeling discussed by participants in prior studies. Zhang et al., participant P5, using the AI is a, quote, combination of fun and frustrating, end quote. Interview I42, quote, I feel like I was more frustrated, end quote, when I worked with Copilot, quote, because I was stuck and I hate that feeling. I had this robot helping me and I couldn't continue even with the robot, end quote. 4 participants, I1, I10, I43, and I47, discussed the idea of dissonance due to a mirage, where AI-generated code deceptively appears correct. However, only 2 specifically mentioned experiencing it despite its appearance in prior work. Scotia, Hacker News, post 35765.407. Quote, nearly every time I've asked ChatGPT for code, it gives me either plausible but wrong code or total hallucinations, end quote. Interview I1, quote, sometimes Copilot would give me a solution that looks almost correct and I would test it and it wouldn't work. That kind of makes it harder when it does do that, end quote. Interview I10, it was confusing when I would change my plan based on Copilot suggestions, quote, but then it wasn't working, end quote. Finally, while participants were not generally fearful about Copilot, some discussed how apprehension might be reasonable based on their interactions, like in prior studies. Prather et al., participant number 15, quote, it might take over the world and write its own code, end quote. Interview I20, quote, I think it might be slightly unsettling how well it can predict things, but I don't think it's a real fear or concern. Interview I43, sci-fi does make me, quote, a little concerned. I wouldn't say I'm seriously concerned about it, but it's something to think about, end quote. In movies, you always see that classic scenario of, quote, robots taking over and controlling life, end quote. Harmony. Despite their negative experiences, participants also mentioned many examples of harmony in interactions. Like dissonance, we chose the code name for this theme, but it has been observed many times previously. For example, references 3, 18, 21, 40, and 51. As in prior work, the most common type of harmony was related to alignment between participants' desires and Copilot's behavior, such as when participants found suggestions helpful. Scotia, Hacker News, post 36091502. Quote, I find ChatGPT to be very helpful for working with programming languages that I'm less comfortable using, end quote. Interview I2, quote, I think Copilot helped me a lot in solving the problems, end quote. Alignment also happened when Copilot provided good clarity or made programming easier. Interview I19, Copilot suggestions were fairly easy to understand. Quote, I like the fact that they included comments themselves, so it makes it easier to read, end quote. Interview I24, using Copilot, quote, made things a lot easier, end quote. Harmony was sometimes exhibited by mention of emotional experiences like calm, enjoyment, and fun. However, participants' positive emotions were generally more tied to their success on programming tasks than on whether they used Copilot. See teleology in 3.4.5. Jayagopal et al., participant P19, quote, I really liked how I could see the suggestion without having to do anything, end quote. Interview I19, compared to working alone, with Copilot there's, quote, less mental taxation on you, so you're more calm, but there's not a super big difference, end quote. Interview I9, for my classes, quote, it'd be nice to have Copilot. I think I would really enjoy using it, end quote. 3.4.3, work allocation. In this section, we describe the 2 behaviors of work allocation undertaken by a programmer using an aid, insourcing and outsourcing. We identify to whom certain work is generally allocated and why one allocation behavior might be chosen over the other. Table 3.5 shows first and second level subthemes of each of the 2 behaviors organized by the number of participants who reported or implied an occurrence of the given behavior or reasoning, event-based to count. For further information on the reporting of prevalence, refer to section 3.2.3 and table 3.5. Insourcing. When a user does work themselves rather than having or letting AI do it, we call this insourcing. This behavior is first named here, inspired by reference 40, but it was observed many times previously. The work participants talked most about insourcing was evaluating AI-generated code. The novices in our study relied heavily on pattern matching to decide whether the code they were evaluating matched what they expected they might need. Barkey et al., participant P6, quote, when I see a suggestion, the closer that suggestion is to the mental image I hold in my head, the more likely I am to trust it, end quote. Interview I10, I would decide to take one of Copilot's suggestions, quote, if it's something that I would write on my own, end quote. Interview I5, often, quote, I had a very specific way I wanted my code to work, and then I didn't really know what Copilot was doing, end quote. However, some also used more careful inspection to decide whether the code looked correct. Jayagopal et al., quote, novices spend time reading and tracing synthesized programs rather than accepting them without question, end quote. Interview I1. Sometimes after I took an inline suggestion, quote, I would look at it for a bit, end quote. Interview I2. I would look through, quote, all the possible solutions from Copilot, end quote. Then I would take one of those and, quote, just try to understand it by reading through it myself, end quote. Because the novices in our study did not always clearly distinguish between running code and testing it, we lumped these together as executing, as in reference 3. Lang et al. 69% of participants reported evaluating suggestions by, quote, executing the code. Interview I-42. I found it, quote, helpful seeing how the test cases went wrong, end quote. Interview I-15. When I get a big chunk of text, I can't tell what's happening. Quote, I just want to take it and see if it works, end quote. A few of our artifacts also fell under the theme of tinkering, an idea we expand beyond using temporary changes for better understanding code to encompass the debugging process as a whole. We suspect that participants engaged in much more of these behaviors than they talked about in their interviews. Also, when participants specifically mentioned changing the code during the debugging process, we categorize that instead as shepherding by adapting. See 3.4.1. Kazemadabar et al. Quote, we identified 30 instances in which learners actively tinkered with the AI-generated code by temporarily changing values, conditions of while loops, modifying syntax, or even temporarily removing code to see how it contributed to the entire program, end quote. Interview I-19. When I was working on the tasks, quote, I would look at the terminal to find the error. I did that often, end quote. Interview I-16. I think that in the future, quote, Copilot could write the code, but then a person would have to go in and find all the exceptions and stuff and debug it, end quote. Other types of work participants discussed insourcing were problem solving, goal setting, understanding, and creativity. Interview I-4. Quote, I do prefer coding alone just because it allows me to think more. Copilot sort of takes away the thinking process a little bit, end quote. Interview I-9. When I decided not to take a panel suggestion, it was because, quote, it didn't necessarily suit what I was trying to code for, end quote. Interview I-10. I wanted to understand Copilot's code because I feel like I wouldn't be able to add on to it if I didn't understand it, end quote. Interview I-47. A lot of times AI-generated content can be, quote, lacking in tone, very lackluster, very generic, and you have to be able to, provide some sort of, expertise to it, end quote. Two participants, I-9 and I-43, used insourcing behavior we call slow rejecting, inspired by reference 40, where they saw a suggestion from Copilot but typed something else to implicitly reject it. Two others, I-10 and I-20, exhibited under-reliance, describing how they failed to get the full benefit out of Copilot due to insourcing too much work. When reflecting on why to insource work, participants cited fun and control as motivators. Interview I-10. I think I would want to try to code on my own before using Copilot. Quote, I feel like it's more fun that way, end quote. Interview I-42. Quote, I had my way and I wanted to stay with that, end quote. Outsourcing. Outsourcing, which was introduced by reference 40, occurred when participants allowed or requested AI to do work for them. The most common type of work participants discussed outsourcing was expression of ideas into code. In prior work, participants mentioned using AI for expression of template or baseline code that they could then change. White et al. Quote, many participants expressed a willingness to accept imperfectly translated code as a starting point, end quote. Though sometimes expression helped with logic, it also helped with writing correct syntax and reduced the need for typing. Ross et al., participant P40. Quote, it helps me to avoid silly syntax errors and can help when I cannot remember exact function/method names and required arguments, end quote. Interview I-16. Quote, you don't have to think of the code as much on your own, especially things like syntax. You don't have to be as particular, end quote. Interview I-47. Quote, I tried to reserve it for cases where I know exactly what I need to do. I just can't be bothered to type it all out, end quote. As in prior work, we identified many artifacts consistent with over-reliance on AI assistance. By Thillingham et al. Quote, we observed 8 instances of over-reliance on Copilot. For example, participant P8 simply accepted the generated code and said, quote, I guess I'll take its word, end quote, end quote. Interview I-5. Quote, there was one where I just really didn't even have to look at the question. Copilot just totally knew what to do, end quote. Our participants recounted their over-reliance on Copilot during the programming trials, such as by using code but not understanding how it worked or not learning the constructs within it. Interview I-24, quote, with some of the tasks that I was doing, I wasn't really trying to understand some of them. I was just entering what Copilot was suggesting, end quote. Interview I-15, even though I saw Copilot use it, quote, if I needed to use the insert function, I'm not quite sure how to do it. I probably wouldn't think of it, end quote. Lastly, participants talked about outsourcing of simple work like repetitive tasks and basic solutions. Weiss et al., participant P4, quote, focus on letting the machine do the stuff that's really easy, end quote. Interview I-9, I used the inline suggestions, quote, a decent amount, especially for the shorter functions or the ones that didn't require that much text, end quote. Interview I-43, in a real-world situation, quote, it'd be much more important to actually think about how you want to do it and then let Copilot autofill more of the repetition type things, end quote. 3.4.4 Appraisals. In this section, we describe 3 types of value appraisals we encountered between prior work and our data. Responsibility appraisals are those programmers use to inform what types of interaction choices are morally upstanding, while self-efficacy and trust in AI are appraisals by the human of the interaction participants themselves. Table 3.6 shows the first level appraisal subthemes organized by the number of participants who reported the given appraisal count. For further information on the reporting of prevalence, refer to section 3.2.3 and table 3.6. Responsibility. Every participant had something to share relating to the theme of responsibility, the idea that there is a right or necessary way to approach use of AI code generators. There were many artifacts stressing the importance of participation by the human user, in contrast to the dividing of work discussed in 3.4.3 above. Participation refers to the value of the human being involved in the collaboration with AI. Weiss et al., participant P6, quote, I might want to have the option to look into what the AI is doing, just so I can interpret or prepare my code better for the translation. End quote. Interview I-24. I might be concerned if the AI were a lot better, but right now I'm not, quote, because it needs your input in order to work, end quote. Interview I-47. You just had to, quote, explain 80% of what it needs to do, just in the comments alone. If for some reason those aren't clear, then you had to start coding it yourself, end quote. Many participants also felt that the context in which an AI code generator is used has a bearing on the appropriateness of doing so. Scotia. Some commenters feel, quote, that ChatGPT and other large language models will soon be able to replace software developers, especially in domains that are not safety critical. Quote, I think it could go either way depending on the product, end quote, end quote. Hacker News Post 35205999. Interview I-13. Quote, a company versus school is very different. When you're in school, you're trying to learn, but in a company, you're kind of just want to do that thing. And so if ChatGPT can help a little, I think it'd be fine, end quote. I-43. Quote, I think if Copilot was allowed, I would use it for code I already understand, but if I came across a problem that I didn't, I would try to figure it out myself, end quote. Several felt that using AI code generators might threaten their integrity or academic honesty. Prather et al., quote, students were uncertain about the implications of Copilot for plagiarism, end quote. Interview I-47. If I can use Copilot to, quote, get the boring parts out of the way, that's fine, end quote, as long as, quote, no one's relying on me to do it by myself, end quote. Interview I-15. Quote, I don't want to use it to my full advantage. I don't want to get an honor code violation, end quote. Others described how the mindset a programmer takes while programming and the maturity of the programmer can determine how good or responsible the usage is. Interview I-24. I might only analyze Copilot's suggestions more deeply, quote, if I had the motivation to learn what it was trying to do, or how to do the things that it was suggesting, end quote. Jiang et al., participant P12. Quote, I can see it being of great use to people who are not that proficient in coding to be a good sort of introduction, or really lower the barrier to entry for coding, end quote. Interview I-42. Right now I'm still learning, so, quote, I want to come up with the solutions myself, But one day, once these really simple codes become automatic, I might as well have a program like this write them for me, end quote. In addition to integrity, several participants cited accountability as a critical value to uphold while using the AI to code. That is, they believed a programmer should be able to answer for the code they deliver. Two participants, I-11 and I-47, thought it was okay to use AI to code in moderation. Interview I-5, quote, I want to be the authority on my own work. If I were ever to have someone ask me about it or I need to modify something, I'd want to be able to fully understand what I had submitted, end quote. Interview I-11, quote, I think trying to code by myself as long as I can would be better, but if I need a suggestion, one little suggestion, not the whole project, that could be helpful, end quote. Self-efficacy. Self-efficacy is a reflexive appraisal of one's own capabilities and potential to succeed at something. It was first discussed in our context in reference 40, but we provide concrete examples of it in action. Over half of the participants exhibited some hint of low self-efficacy in relation to using Copilot. Often, this was because participants did not feel they could take credit for the successes they achieved with Copilot's help. Interview I-11. When I used Copilot, quote, I felt like I gave up more quickly. I relied on Copilot too much, which I was not happy about, end quote. Copilot would make me more efficient, but I think my confidence in CS, quote, dropped a bit. Because isn't the point being able to do it on your own? End quote. Interview I-47, quote, I don't think it could ever be satisfying to use Copilot. I don't know how something can be gratifying when something does something for you, end quote. Not only did participants struggle to take credit for successes with Copilot, but subtle comments indicated their self-blaming when they encountered struggles with Copilot. Nam et al., participant P28, quote, I think I just didn't word the question well, end quote. Interview I-2, I don't think Copilot ever made it harder to program, quote, I just have to explain the question more clearly and then debug what Copilot gives me, end quote. Interview I-9, when, quote, Copilot wasn't necessarily giving me what I was looking for, there was a little bit of friction, but I wouldn't consider it friction between me and Copilot, I just consider it friction between, my thinking, end quote. A few other comments about self-efficacy did not quite align with low or high self-efficacy. In these cases, participants described that programming alone is more satisfying than using Copilot, but not that using Copilot is unsatisfying. However, they do shed light on how over-reliance, see 3.4.3, might degrade self-efficacy over time. Interview I-19, quote, it was less satisfying on the tasks that I didn't do myself, end quote. But there were also ones, quote, I did myself and I thought through, and then adding Copilot, end quote, to speed things up, quote, doesn't make it any less satisfying, end quote. Interview I-43, quote, it's more satisfying to come up with the solution yourself, just a sense of accomplishment, end quote. On the other hand, several participants' comments indicated high self-efficacy in relation to using Copilot. Some felt that they deserved credit for success with Copilot when their shepherding played an integral role. Others felt that assistance and stimulation from Copilot would improve their confidence throughout their CS learning path. Interview I-12. It was a good feeling when Copilot helped me get unstuck. But really, quote, it was just me giving it the correct prompt, end quote. Interview I-20. Knowing I could get more practice by using Copilot would help my confidence in CS, because if, quote, I were coding randomly in a file, I don't know where I could go with that. But with Copilot, I guess it could give me different directions or things I could try. It's kind of like a stimulus in that way, end quote. Trust in AI. Only 5 participants shared comments that related to trust or confidence in Copilot. I-2, I-24, I-43, I-4. Both prior work and the limited data we have suggest that users place some level of initial trust in AI. Prather et al., quote, novices tend to view feedback in programming context to be the truth and the systems generating it to be infallible, end quote. Interview I-2, quote, I believe Copilot has a better programming sense compared to me, end quote. Interview I-43, I didn't usually try to fully understand Copilot's suggestions, quote, I just kind of trusted Copilot, end quote. I think of it like a, quote, database of lots of good code, end quote. So I would assume that its solutions are, quote, probably better solutions than I would come up with for the most part, end quote. Then this initial level is either reinforced through harmony or broken by dissonance over time. Bythillingham et al., participant P7, quote, "At this time, I probably prefer IntelliSense just because I trust my own Googling and understanding code examples online rather than opaque suggestions from Copilot," end quote. Interview I-24. After working with Copilot, quote, "I'd say I feel better about Copilot and its suggestions than I did before," end quote. Interview I-4. At some point, quote, "I lost a bit of confidence in Copilot because I was trying to try out different things, but Copilot was generating the same answer," end quote. Interview I-20. Copilot can, quote, "be distracting just in deciding which approach to take," end quote, "but I think it can get better at knowing, quote, when to trust what I am going with," end quote. 3.4.5 Anthropomorphism. In this section, we describe the opposing perspectives programmers can take with respect to AIDE's anthropomorphism, i.e., whether it is an inanimate technical object, objectivizing, or a human-like character, humanizing. In addition to the plain content of participants' comments, subtext especially helped to capture these perspectives. Table 3.7 shows first-level subthemes organized by the number of participants whose comments aligned with the given theme, count. For further information on the reporting of prevalence, refer to section 3.2.3 and table 3.7. Objectivizing. We identified that participants generally created objectivizing conceptualizations of Copilot, classifying it as a neutral technical object rather than a persona. Interview I-20, quote, "Overall, my feelings are probably neutral. I think it's helpful for users to get practice with it and learn how to use it well to their advantage," end quote. Many objectivizing comments simply displayed participants' emotional dispassion towards Copilot or AI in general. Interview I-13. When Copilot can't help, quote, "I wouldn't say it's super disappointing," end quote. And when it did, quote, "I was just like, quote, okay, it was enjoyable, but it wasn't mind-blowing or anything," end quote. Interview I-5. "It didn't really get in my way because, quote, I'm not that good of a coder, so it's not like I'm like, quote, oh my gosh, it's messing my rhythm up," end quote, end quote. Many comments also captured the inconsistency of experiences with Copilot. Sometimes it was very helpful, while other times it was not. Ross et al., participant P19. Quote, "The code generator was good, but you still have to really check it," end quote. Interview I-12. Quote, "I think working with Copilot was good in some cases, but not good in other cases, especially," end quote, "on the, quote, tasks where I didn't fully understand the question," end quote. Interview I-16. Quote, "It was either like Copilot just solved the problem for me and I didn't do anything, or I kind of solved it and then along the way Copilot would help me," end quote. Several participants referred to Copilot as a tool or resource for them rather than personifying it. Interview I-9. "It was comforting to know that Copilot was, quote, kind of like another resource that I could use," end quote. Interview I-4. Quote, "I think it was worse programming alone than with Copilot, because that's one less tool I was able to utilize," end quote. A handful of objectivizing comments demonstrated subscription to a teleology of programming also present in prior work, that the means used to write the code only matters insofar as it progresses the user towards successfully achieving the end goal. White et al., participant P2. "I would, quote, be happy with the NMT model," end quote, "as long as, quote, I get the correct output," end quote. Interview I-19. Quote, "I think my feelings stayed pretty consistent throughout, a little bit better when you have more success with it," end quote. Interview I-47. "The only triumph I had was, quote, getting to pick myself back up after," end quote, "getting stuck on one. I got a similar question later and, quote, I was like, quote, okay, I'm not an idiot. I do know this," end quote, end quote. In line with prior studies, two participants, I-1 and I-12, objectivized Copilot by not blaming it when things went poorly in interactions with it. Scotia, Hacker News, post 36087083. "What ChatGPT gives you is, quote, not perfect code, but it's the right idea," end quote. Interview I-1. "When Copilot leads me astray and I have to restart, quote, it depends on probably what the problem is and how familiar I am with it, but I probably would try to use it again," end quote. Interview I-12. "Sometimes Copilot didn't help, but, quote, if I don't understand the question, then like, I don't know what I want, so Copilot can't know what I want, right?" End quote. Humanizing. There were several cases of participants humanizing Copilot by implying it to have human-like traits as in prior work. This theme was a relatively rare way to think about Copilot, with just under half of our participants doing so. Prather et al. Quote, several participants reported that they felt Copilot was aware, knowledgeable, and had agency, end quote. Interview I-15, quote, it felt like a little sibling. You know, they're like, quote, let me help, end quote. I want to consider it my friend, but I'm a little scared, you know, end quote. Interview I-2, quote, I guess I can just explain everything to it so it can understand me more clearly, end quote. 3.4.6, Prior Knowledge. In this section, we discuss the final topic, prior knowledge. As this topic is considerably smaller than the others, its top-level themes are more comparable in size to other topics' first-level subthemes. However, we emphasize this portion of the results for its centrality to the engineering of human-aid interaction. Beyond improving aids themselves, education is a primary mechanism for molding human-aid interactions to match individual, organizational, and societal standards. Table 3.8 shows first-level subthemes organized by the number of participants whose comments aligned with the given subtheme, count. For further information on the reporting of prevalence, refer to section 3.2.3 and table 3.8. Expectations. Participants were asked directly about how their expectations compared to what they experienced. Their answers reveal that their preconceptions guide their actions and sometimes fail to match reality. Liang et al. Quote, participants developed mental models of these tools, as they reported leveraging existing code as additional data for the AI programming assistant to use, end quote. Interview I-11. Between programming, quote, on my own versus doing it with Copilot, I realized I liked it more by myself, which I was not expecting, but I'm happy to know that now, end quote. Interview I-13. Copilot, quote, didn't help that much, but I thought it would help, so that was an interesting contrast, end quote. 3 participants, I-19, I-20, I-47, described underestimating Copilot's abilities. As in prior work, this can happen when users have not yet experienced the benefits of a new tool. Gardella et al., participant P6, after using flash fill in Excel. Quote, oh cool, that was easy. I didn't know for sure if it could figure out the pattern from one example, end quote. Interview I-47, things, quote, went pretty much as expected, maybe slightly better. It needed less than I thought it would. Going off the comments alone was kind of insane, end quote. One participant, I1, described overestimating Copilot's abilities, which happens when users are hopeful about an aid's utility. Barkey et al. Quote, Twitch streamer S3 expected the multiple suggestions to be diverse and was sometimes disappointed when they were not, end quote. Interview I1. I thought, quote, if I were to just type a few basic instructions, it'd be able to do the rest for me, which it was not, end quote. Biases. Participants also described biases they had toward AI, such as I-43's encounters with sci-fi movies, see apprehension in 3.4.2, or I-15's having seen a video on social media critiquing generative AI in the popular productivity app Notion. Similarly, participants in prior studies have been biased entering into interactions with aids. Ross et al. Quote, people told us about their frustrating experiences with conventional chatbots and raised doubts about the knowledge, capabilities, and value of conversational programming assistant, end quote. 2 participants, I-12 and I-13, mentioned being biased by incorrect AI behavior shown in the training videos for the study. Similarly, Jiang et al. Mentioned how training can help to bias users' expectations too. Jiang et al. Quote, in onboarding materials, it may be helpful to show different categories of requests that users may expect to work well, but that surprisingly don't, to help calibrate expectations, end quote. Competencies. Finally, users' existing competencies inform how they use aids. This relates to the idea of shepherding as an acquired skill, see 3.4.1, but also encompasses how general programming abilities impact one's readiness to use aids. Gardella et al. Quote, participants did not always know how best to specify their intent to the synthesizers they used. In particular, what kinds of specifications were best for a given synthesizer, end quote. Interview I-12. I think Copilot would help me a lot with programming assignments, but, quote, only because I have so much experience with it. If someone has, like, no coding experience, they won't be able to manipulate it, end quote, to give it them what they want. Interview I-15, quote, "You still kind of need coding experience. If I had this at the beginning of the semester, I would have been so confused," end quote. 3.5, discussion. 3.5.1, RQ1, how do novice programmers and aides interact while programming under time pressure? We found that novices' goals and values encourage them to steer interactions with GitHub Copilot, yet they were also highly submissive to Copilot's direction. Copilot often acted more like a pilot, leaving the human to second in command. The data showed mixed interaction quality and propensities toward the passive side of several thematic dimensions, including bimodal interactions theory, leadership and intentionality, and the allocation of work within the team. Planning. Barkey et al. Developed the bimodal theory of interaction to describe how novices interacted with GitHub Copilot either for acceleration or exploration. The exploration mode, they say, helps users to, quote, "plan their code actions," end quote, while the acceleration mode helps them to, quote, "execute their planned code actions," end quote. In our looser interpretation, acceleration would be better described as helping users to efficiently execute some coding action, not necessarily of their own choosing. Plenty of studies have described behaviors consistent with acceleration and exploration. Participants in the present study also shared comments aligning with both modes, but they more often reported manifestations of acceleration. This can be explained by the mindlessness demonstrated by participants' lack of planning and intentionality. Acceleration allows code to be produced quickly and with little thought, but exploration provides more fruitful benefits such as enhanced planning through consulting and overcoming the barriers of getting started or getting unstuck. Further, a focus on speed leads to rushing that prioritizes timeliness over understanding, overemphasizes salient UX features, tunnel vision, and encourages short-sighted thinking, myopia. These forms of mindlessness can compound on existing tendencies toward approaching programming tasks with no strategy. We argued that our participants used the exploration mode less because they were rarely developing plans of their own. Ability level is likely relevant here, as the original theory of Bark et al. Was developed against data from renowned programming live streamers and participants with strong programming backgrounds. Advanced programmers have additional competencies for planning and considering possible approaches they might use to complete a task. This aspect of prior knowledge allows them to take advantage of the powerful exploration mode with an aid rather than mindlessly taking suggestions to simply feel like they're progressing. Authority. Our results suggest that a user's authority over an AI interaction is a precursor for effective planning. Our data showed that not only were participants shepherding the AI, but the AI was influencing them in return. The prevalence of shepherding demonstrates that participants were active collaborators in the interaction. Prior work also provides strong evidence for this conclusion. Though delving into the types of shepherding participants used, prompting, adapting, and backtracking were most prevalent. That is, participants were telling Copilot what they wanted and coping with its responses as opposed to leading the problem-solving effort. This sometimes led to drifting from one wrong solution to another, which, like tinkering, we suspect happened more often than participants discussed. We labeled much of our data reminiscent of drifting instead as shepherding, dissonance, mindlessness, or influencing, since seldom did participants provide a perfect match for our definition of drifting, a maladaptive and wasteful form of shepherding. Regardless of the naming, it's clear that AIDEs can disrupt the natural thinking process by polluting it with new ideas, tempting users to take shortcuts, and squelching the uniqueness of one's own coding style. Prather et al. Found similar patterns, by which generative AI disrupted novices' metacognition by, quote, misleading and, quote, interrupting them while they were trying to code. For novices, these disruptions may outweigh benefits like exposure to technical variety or the AI's potential for teaching them through its suggestions. Notably, our analysis showed no examples of decomposition and almost no examples of slow accepting. We reason about these as more adaptive forms of shepherding, in which a user displays authority by slowing down to think and plan their approach. It's fitting then that mindless and submissive novices with limited prior knowledge would be unlikely to engage in these practices. Several prior studies with participants of ranging ability levels reported examples of decomposition. But of these, only reference 21 enforced time pressure, the most relaxed form of studies with time pressure. Thus, when time is of the essence, decomposition may be the first form of shepherding to be abandoned. Unsurprisingly, slow accepting is also not an ideal strategy when a faster alternative is clearly available and preferable. Finally, the data supporting shepherding as an acquired skill further emphasize the importance of competencies and expectations for successful interactions with aids. Studies have repeatedly supported that working proficiently with an aid is a non-trivial and challenging art. Without sufficient prior knowledge entering an interaction, a novice is not ready to perform at their best in a team with AI. The original quantitative results from this study support the same conclusion. Work allocation. In addition to outsourcing work to GitHub Copilot, participants also demonstrated insourcing of work, i.e., doing it themselves instead. Participants' choices showed some promising leadership of Copilot through insourcing of pivotal aspects of software development like problem solving, goal setting, and understanding of the code, while outsourcing shallower tasks, simple work, and expression of ideas into programming language. However, these data are overshadowed by numerous manifestations of over-reliance and insourcing's largest sub-theme, evaluating. Assessing the quality of AI-generated code is surely an adaptive strategy, but it's also a reactive one, whereby the human user is responding to the activity of the aid as opposed to the reverse. Such a dynamic creates the conditions for mindless drifting and influencing to occur. What is more, the top evaluation strategy used was pattern matching, a faster alternative to inspection. Rather than reviewing the details of the code, a user simply skims the code to find the expected pieces of text. Though often effective, this technique suffers from two major drawbacks. First, in the case of a mirage, a human can believe that the code is correct, missing small issues that are not readily apparent. Such oversights are also part of why humans experience overload when aid interfaces are too complex or verbose. Secondly, a user's prior knowledge heavily restricts the space of possible outputs from the aid they deem acceptable. Their expectations, biases, and competencies impact what they expect AI can or should do. For example, section 4.3.1 describes how participants judged Copilot's behavior against what they would do alone. The obvious problem is that, as novices, what they would do alone might not necessarily be optimal. It follows that the ability to experience benefits from using an aid such as interaction harmony or exposure to a variety of programming constructs is restricted through rejection of suggestions that could beget those benefits. Rapport. Participants did, nevertheless, experience harmony with Copilot as in many prior studies. In general, the quality of their experiences came down to alignment versus misalignment. When Copilot offered helpful suggestions that provided good clarity, this made it easier to program. The significantly lower effort and mental workload reported in the original quantitative results from this study further support this claim. However, Copilot just as often provided unhelpful or incorrect suggestions that caused confusion and overload, if not enabling mistakes of participants' own. In some cases, participants' biases and expectations played into the quality of their interaction experiences. For example, apprehension about the future of AI was, in one case, fueled by dystopian imagery from popular culture. Enforcing conditions of time pressure, we pushed participants to their limits and uncovered the unfortunately two-sided nature of programming with AI. Forced to make real progress with the aid, participants were less biased by the pleasantries and novelty of casual aid interactions like those in other prior studies, for example, references 40 and 43. In contrast to our expectations from prior work, harmony and dissonance did not often manifest as emotional in nature, nor did participants engage in humanizing the aid quite like objectivizing it. Again, the quantitative results corroborate this finding. 3.5.2 RQ2. What factors can explain how novices use aids while programming under time pressure? Time pressure. Time pressure, a la rushing, added another layer to interaction dynamics. Expressions of mindlessness, for example, tunnel vision and myopia, came from the apparent drive of a novice to take immediate action in pursuit of progress. Consider the programming of a basic iterative process. An advanced programmer might choose between a while loop, a for loop, a higher order function, or a recursion. A novice, by comparison, might only know a standard for loop. Since the novice knows only one approach, the most efficient step they know to take is the one that feels most like progress, getting more code into the editor. Planning efforts feel unproductive and wasteful to a novice when they think they know only one way forward. This exacerbates over-reliance, mindlessness, and the power of influencing. When polluting occurs, it can be difficult for a novice to, quote, dislodge a mental model that is incorrect. Further, because of pattern matching to a small set of expectations, novices have limited openness to AI's advice even as they are swayed so strongly by it. Rushing also encourages drifting. By mindlessly taking easy actions, novices miss the hidden value of variety and helpful suggestions that could be obtained by taking a little more time for exploration. If they lose a sense of how close they are to being done, they might choose to ignore potentially useful suggestions that change their approach fundamentally. Only when they find no way forward do they resort to backtracking, looking again for quick solutions. Prior knowledge. As discussed throughout 3.5.1 above, prior knowledge lays a key foundation for a novice's interaction with AI. Along with demonstrating the power of GitHub Copilot, the training we gave participants showcased Copilot's fallibility, giving at least 2 participants biases against brazenly following its suggestions. Competencies and expectations further mediated interactions by determining what novices knew how to do with AI, how much leadership they could provide to it, and how they then reacted to what happened. In section 3.5.4 ahead, we discussed the potential of educational training to strategically build prior knowledge for users. Values and necessities. In line with prior studies, participants shared extensively about the meaning of responsibility when working with aides. They felt that collaborative participation with the AI was both necessary and upstanding. One might suggest that the technical limitations of this particular AI materialization fueled this sentiment, yet amidst rapid technological progress, automation has for decades rendered humans, ironically, responsible for vigilant supervision and intervention after failures. We argue that a combination of pragmatism and moral conviction will continue to justify human participation in AI teams even as technology continues to advance. Novices in the present study discussed integrity and accountability as values relevant to using an aid and noted that maturity, moderation, and context impact their appraisals of human aid interactions. These findings lead to the conclusion that unfettered, no moderation, use of AI by novices, low maturity, in an educational context is morally disfavorable, even to the novices themselves. Within the experimental context, participants only somewhat lived out their values. While believing that insourcing of heady work like problem solving, goal setting, and understanding was important, these seldom manifested during the trials. Participants' reactive insourcing, see 3.5.1, suggests that they primarily did work out of necessity rather than desire. They mentioned that control and fun could motivate insourcing, but the tempting prospect of easier progress with Copilot often led to outsourcing instead, in some cases to a point of over-reliance. This result is consistent with the findings of Prather et al., who found that struggling novice programmers showed an, quote, illusion of competence, end quote, by which their actions did not match their beliefs. It was reasonable to assume, though, that typical values and motivations should not apply in this situation. Participants were specifically instructed to complete as many tasks as possible and use the AI as much or as little as needed to maximize productivity. Evidently, participants felt sufficient trust in AI to rely on it heavily for this purpose, unless given some reason not to. Herein lies a critical aspect of our study design that we believe muted the role of trust in participants' choices. Participants had provided test cases against which to measure the AI's performance objectively. By comparison, Ross et al. Did not give participants any running or debugging capabilities, requiring participants to build subjective trust in AI through communication or other means. In other words, programmers act based on feelings only in the absence of sufficient informative logic. 3.5.3 RQ3 How does using an aid under time pressure affect a novice's thoughts and feelings? Mild reactions. In general, participants seemed largely unaffected by their interactions with AI. They experienced some of the best and worst of what Copilot had to offer them. See 3.5.1. We saw this translate to their acknowledging its inconsistency of performance and not blaming it when dissonance occurred. Along with the dispassion that came through in their comments, many participants referred to Copilot as a tool or resource rather than an intelligent agent. Others subscribed to a programming teleology, in that they felt strongly about Copilot only based on the extent to which it helped them to complete tasks successfully. Together, these findings led us to conclude that novices under time pressure tend toward objectivizing an aid rather than humanizing it as suggested by prior work. Participants did, however, sometimes exhibit humanizing by comparing Copilot to humans or applying traits to it like intelligence and understanding. We do believe that aids with more anthropomorphic features, such as GILT, or newer versions of Copilot with Copilot Chat, can better encourage humanizing. Seeing AI in this way has the potential to help users better relate to and use aids, but might also cause inappropriate expectations and behaviors. As discussed in section 3.5.1, the quality of a participant's experience with Copilot was determined primarily by alignment of their thoughts and intentions to Copilot's suggestions. A few participants felt frustration, enjoyment, or peace working with Copilot, but participants did not typically have emotional reactions to the quality of their interactions, as expected based on prior work. The quantitative results back up these findings. Copilot had a non-significant effect to reduce frustration compared to the control condition. That is, Copilot may have reduced some of the tension and frustration associated with programming, but introduced new issues offsetting the reduction. Self-efficacy. Our data showed that an aid can have both negative and positive impacts on novices' self-efficacy, but evidence of low self-efficacy was more prevalent than high self-efficacy. In line with quantitative results, there was no overwhelming effect of GitHub Copilot to increase participants' appraisal of their abilities, but they did build self-efficacy by honing the acquired skill of shepherding and observing its effect on their performance in a team with Copilot. Some also felt increased confidence to succeed in CS, knowing they could use aids as an additional learning resource. However, something not captured in the original results is the self-blaming novices did when noticing poor team performance as a result of poor shepherding. Additionally, they did not always feel they could take credit for successes with Copilot, describing it as unsatisfying, or as at least as less satisfying than working alone. In a few cases, they even experienced emotional dissonance in the form of emptiness and shame about accepting its help. The potential self-efficacy harms of aids are especially alarming in light of the finding by Margalou et al. That students who used aids most during an introductory programming course had the lowest self-efficacy. That is, those students whose self-efficacy is already low may face greater self-efficacy harm from aids as compared to students with higher baseline self-efficacy. 3.5.4 Implications and Recommendations. Based on our findings, we recommend that educators prepare computer scientists to work in hybrid intelligence teams according to two-pillar learning objectives. 1. Maximizing useful output of the team. 2. Preparing to intervene when needed. Teach effective shepherding. Educators must prepare students for productivity-focused roles where they may be allowed, encouraged, or required to use aids. Over decades, the software development industry has become increasingly motivated to produce software quickly and efficiently. The ability of aids to improve programming performance and empower less skilled programmers to produce useful code undoubtedly creates economic pressure for companies to adopt aids urgently. CS education will need to adjust to these conditions with similar urgency. Without specific instruction, the novices in the present study took time to adjust to using Copilot and ultimately gravitated most toward mindless and submissive strategies. The quality of LLM-generated code depends heavily on the quality of the inputs provided, and as in reference 21, our results showed that users can discover this through experience. UX researchers are working to make aid interaction more intuitive, but students still need to learn and practice this skill. Additionally, our results suggest that doing so can provide a new way for students to build self-efficacy. Notably, our participants did not naturally tend toward problem decomposition, a critical step in solving real-world problems, and the focus of a full chapter in Porter and Zingaro's AI-assisted programming textbook. Pedagogical approaches akin to, quote, prompt problems, end quote, can help to isolate different types of shepherding so that students can avoid overusing some over others. For example, decomposition could be targeted by having students rewrite correct prompts to better specify subgoals, or adapting could be targeted by having students modify AI-generated code. Ensuring that the code students learn to produce with aids is useful also requires that students learn to use aids for a broad range of tasks. When Copilot could not produce a full solution for a participant, they would generally do high-level tasks, for example, problem solving, and evaluation of code themselves, while using Copilot for shallower tasks like expression of ideas into code. Students need instruction on how to utilize Copilot for the tasks they otherwise only know how to do manually. without fully relying on Copilot for an entire task. They can then recognize a wider range of opportunities to apply AI assistance, for example, testing, documentation, algorithm development, and do less work while remaining engaged. Enable human intervention. Educators must teach students why and how they should participate in software development in the age of AI. If strong human direction led automation to flawless performance, it would be the only necessary competency. However, aids can produce code that fails to meet functional requirements, for example, correctness, reliability, and scalability, or non-functional requirements, for example, originality, style, and readability. Further, programmers may lack access to aids due to temporary outages or permanent financial or legal constraints. For these reasons, well-rounded programmers need to be able to supervise aids and code without them if needed. The novices in this study relied heavily on GitHub Copilot to accelerate their programming, exacerbating aimless programming behaviors and harming self-efficacy. When reflecting on the experience, many identified how fast pacing and over-reliance made it challenging for them to fully scrutinize and learn from AI-generated code. We suggest 3 instructional thrusts to counteract these tendencies. First and foremost, educators can introduce students to the latest aid technology, how it works, how to access and use it, and what its implications are. Second, educators can prohibit the use of aids for some assignments. This will incentivize students to learn from AI when they can use it, rather than to simply maximize productivity. It will also allow them to build self-efficacy by recognizing their abilities independent of assistance. Third and finally, educators can provide specific instruction on interventions to AI-generated code. For example, the approach in Porter and Zingaro's textbook provides introductions to reading, testing, and debugging AI-generated Python code. Our participants' propensity toward the pattern matching evaluation technique points especially to a need for teaching reading and testing competencies. We saw some evidence that our training on Copilot's fallibility made an impression on our participants, but they only truly learned to cope with this from first-hand experience. For this reason, we suggest that students be intentionally exposed to erroneous AI outputs so they can learn to slow down, approach large suggestions with caution, and inspect code carefully. 3.6. Limitations. Because our data was collected from the participants of our prior study, the limitations discussed in the original paper also apply here. Our instructions to participants to prioritize productivity present an additional threat to ecological validity, as real students typically have some motivation to learn. However, we hope that this design choice sheds light on how students might compromise on their values in service of meeting a deadline or acing an assignment in a worst-case scenario. Furthermore, our qualitative approach introduces several potential threats to validity. Research biases certainly shaped the outcome of our investigation, as is expected when drawing on reflexive qualitative methods. To mitigate the effects of our biases, we attempted to avoid loaded or leading wording in interview questions and performed member checking of participants' responses. We also drew on analysis and internal critique amongst 3 researchers when formulating the early versions of our framework and selecting meaningful quotes. While the organization and emphasis of the ideas in the framework are highly subjective, we demonstrate the validity of the ideas through a strong basis in existing literature and the use of direct quoting. Our IRB does not permit public release of our raw data, but does allow us to share it with other researchers upon request. Finally, because of differences in personality, language abilities, interview length, expressiveness, etc., we were concerned about overrepresenting certain participants in our analysis. To counteract selective reporting, we attempted to balance the use of direct quotes across participants. For transparency, readers can review our selection statistics in Appendix C. 3.7. Future work. Future work can focus on testing our framework and exploring the efficacy of instructional approaches to carry out our recommendations. Because our framework was co-constructed out of both prior work and our dataset, different ideas might be emphasized when considering different groups of students or different experimental conditions. For example, it remains to be seen whether novices who are incentivized to learn would do so when using an aid under time pressure. It's also unclear how specific our participants' attitudes are to their unique educational and cultural backgrounds. Regarding pedagogy, we're only aware of one formal approach to teaching AI-assisted programming. It's intended as an introduction to programming that encourages using aids from day one. Further effort should be made to craft curricula that utilize aids in different ways and for students of different ability levels. 3.8 Conclusion. In this article, we synthesized a model for human-aid interaction from existing literature and analyzed qualitative data from 17 semi-structured interviews to assess and extend the model. We validated numerous themes from prior work, including acceleration, shepherding, exploration, mirroring, dissonance, harmony, outsourcing, and humanizing. We also formalized several other themes, including mindlessness, influencing, insourcing, responsibility, and objectivizing. Our results stress the importance of novices' value appraisals and prior knowledge for determining outcomes, but also show that novices often act against their values when placed under time pressure. We acknowledge the subjectivity and limitations of our framework and encourage other researchers to further assess our findings. Our educational recommendations are for instructors to include aids in their curricula through both performance-centered aid-permitted assignments and solo assignments for building independence and aid intervention skills. Future work can explore applied pedagogical approaches for hybrid intelligence teaming and examine the effects of learning-based incentives compared to performance-based incentives on novices' interactions with aids. Acknowledgements. This work was supported by the UVA Distinguished Fellowship, NSF NRT 1842490 and GRFP 1829004, and the Virginia CCI CVN GR 102900. We thank Claire Sabula and Ashraf Ibrahim for their assistance with analyzing this data and developing our framework.